So the next talk is on slightly different title, on phase transition algorithms for the Ising model, and Piyush will present the talk.
Thanks. Yeah, so I'm going to be giving mostly a survey of sorts of some results which relate phase transitions to algorithms for the Ising model. And I'm going to be talking mostly about algorithms for general graphs. There's a huge literature on looking at algorithms for the Ising model on specific lattices and very deep results connecting those to the phase transitions of the Ising model. But we'll be looking more in the context of general graphs, maybe with just some degree bounds, and seeing what different phase transition notions get us. So just so that we are on the same page, what is the Ising model? So it was one of the first stylized models for studying phase transitions. In particular, the phase transition that magnets show, which is of losing their spontaneous magnetization when the temperature goes beyond a certain fixed temperature called the Curie temperature. And this was proposed by Lenz in 1925, but it's called Ising. It looks something like this. So as I said, it's a very stylized model for a magnet. So the magnet itself is modeled as some kind of a graph, usually in these contexts a grid. And the nodes in the graph sort of represent some kind of domains. They have two kinds of spins, plus or minus. And there is some parameter j which sort of represents the inverse temperature. So this is kind of thing we've seen in previous class. And what the model does is it puts a probability distribution over all configurations, over all such assignments of plus and minus spins to the vertices. And this probability distribution is given in terms of this kind of a formalism. So there's an energy term which is just you sum over all the edges, the product of the spins. So that's like, so each differing edge contributes a -1, each agreeing edge contributes a +1. You multiply it by the interaction or the temperature parameter, and then the probability is supposed to be exponential in this. It's proportional to exponential in this. And then it's supposed to be a model for magnetization. So where is the magnetization? The magnetization would be some kind of average here. So it would be the average, for example, of the sum of the spins, where the average is taken with respect to this distribution. So that's the classical Ising model as it was proposed. Since then, it has of course become quite ubiquitous outside statistical mechanics as well. It appears in a wide variety of areas for different reasons. For example, in choice theory, it appears as a logit response, or in other words, and that's basically because logit response is the same as something called the global dynamics. For the same reason, it's also used for modeling spread of opinions in networks. It's also used in computer vision as some kind of a proxy for cuts in images. And this is not surprising because it's the simplest maybe example of a very large class of distributions called probabilistic graphical models. And the crucial property that the model has is this one, that if I look at the state of any one node in this probability distribution, then it's independent of all the other nodes conditioned on its neighbors. And that is sort of a consequence of the form of the Gibbs distribution. But this property can be just looked at in more generality, and that's the whole subject of probabilistic graphical models. And more generally, what you want is that you have some set of random variables, in this case the spins, which sit on the nodes of a graph. And you have the following property that whenever you have three sets of those random variables, S, U, and T, such that in the graph U separates S from T in terms of the graph connectivity, then the states on S are independent of the states in T conditioned on U. So the Ising model has this property. So what I said earlier was just a special case of this. And once one has such a graphical model, and there are several questions that arise in applications, and they are sort of related. So two of them that we will look at, or we will not look at so much, but which are related to what we will actually be looking at, are approximately sampling from the distribution. So given such a distribution in some way, given some description of such a distribution, you might want a fast algorithm to sample from the distribution. Similarly, you might want some algorithm to approximate marginals of the distribution. So this would, for example, be the question of approximating the magnetization of some kind of illusion. Both of these things turn out to be related to this problem of approximating the partition function, which we'll see next, and which is what will concern us for the rest of the talk. And there are, of course, other questions that one can ask about this. One of them is to learn the model. So maybe someone just gives us the realizations of the random variables. Maybe we just get the spins, and we want to learn what the interaction parameter is or what the underlying graph is. So that we won't be talking about, but that's another kind of question one could ask about such systems. So for the rest of the talk, I'll be focusing on the partition function.
Sorry, this Markov condition certainly, I mean, it works in the case of spin pair interaction, but also for many body interactions.
Yes. In fact, yeah. So if you allow many body interactions, then they're essentially equivalent. This and so that's the Hammersley-Clifford theorem. Okay. So for the rest of the talk, I'll work with a slightly different parameterization of the Ising model, which is easier to work with for algorithms. So again, I'll not have grids, I'll have general graphs. Given a graph, again the configurations will be plus and minus spins, and I'll have two parameters. So there'll be a edge parameter, which is some sense a proxy of the inverse temperature, and a field parameter, which is, or vertex parameter, which will be some sort of proxy for a field. But the precise way I will use this parameters is the following: that the configurations, this plus minus spin assignments, will get weights proportional to this quantity. So given any configuration sigma, there will be a factor of lambda raised to the power the number of plus spins in that configuration, and beta raised to the number of those edges that are cut, in the sense that they have opposite spins on their endpoints. So the red edges in this term. So for each sigma, I have such a weight function, and then the partition function is exactly the normalization constant that you put in front of these weights to make it a probability distribution, and that's just the sum of these weights. And the question we would be looking at is approximation of this quantity on an input graph G when beta and lambda are fixed. And we'll be looking also at two different. So this also was in the talk in the morning. We'll be looking at two different qualitative regimes of the Ising model, the so-called ferromagnetic regime, which corresponds to beta less than 1 in this parameterization. Here you sort of, the distribution biases itself to those configurations which have agreements on edges. And similarly, the beta bigger than 1, which in this parameterization corresponds to the anti-ferromagnetic regime. Here the distribution biases itself to those configurations which try to differ on neighbors. In terms of computer science, anti-ferromagnetic Ising is something like max cut, it's supposed to be high. Ferromagnetic is something like labeled min cut, which is supposed to be trivial, but that's just a cartoon. So any questions so far?
That last line, beta less than 1 and greater than 1,
yeah.
Would mean 0 rather than 1?
No, so this line is log beta. Sorry.
No, underneath it.
So no, I mean beta less than 1 and beta bigger than 1. Yeah. Because so this beta is like the e to the power 2j in the usual parameterization.
Oh, very bad choice.
Yes, sorry. Yeah, so beta will be between beta. So whenever I'm talking about real beta, it will always be positive. At least most of the time, and it's in the usual parameterization, it corresponds to e to the power 2. So this is pair interactions, but so we had this question earlier. So we can also talk about many body or higher order interactions. So in general, instead of a graph, one can have an hypergraph. So where each edge can have more than 2 vertices. Each hyperedge can have more than 2 vertices. The configurations still are assignments of pluses and minuses to the vertices. And now one can have hyperedge potentials. So these would basically assign to for each hyperedge, it will look at what the spins of the vertices are and assign a weight. And one can also have vertex potentials. These correspond to the lambdas earlier. And then the partition function is just the sum over all configurations, product over all the hyperedge of the hyperedge potentials, and product over all the vertices of the vertex potentials. So we'll also look at these more general things. And the kind of approximation that we would want for the partition function is this kind of what we call fully polynomial time approximation. So given the graph and some accuracy parameter epsilon, we would want to output an approximation which is within a relative error epsilon of the actual value. And we would want to do this in runtime that is polynomial in the size of the graph and 1 over the accuracy parameter. So one could ask for a stronger condition of being polynomial in log of the inverse of the accuracy parameter. But that essentially becomes exact computation, which is just complexly theoretically hard for all the problems that I'm going to talk about. There's a related notion of this, which is the randomized version of this question, which is that your algorithm is allowed to use random bits, and now it has a separate parameter delta, and it is asked now to have the same guarantee as before, but only with probability 1 minus delta over the toss of its own random quants. And the runtime now has to be polynomial in the size of the graph, 1 over the accuracy parameter, just as before, but in the logarithm of 1 over that. So this is a related notion that sort of we won't be looking at much, but it's good to compare it against this. So I said earlier that there's a tight connection between the problem of approximating the partition function and the other questions about graphical models like sampling and computing marginals that I talked about. So here is just a dictionary that holds in many cases, including the Ising model on graphs, which is that sort of partition function sort of corresponds to Gibbs measure, and approximating the partition function corresponds to approximately sampling from mu, in the sense that if one has an efficient algorithm for one, then one has an efficient algorithm for the other as well. So this holds for a large class of problems called so-called self-reducible problems. The Ising model is not one of them, but it's known that it holds for this as well. So, and this dictionary has been used for many of these classical algorithms that do approximate the partition function. And what they do is use the dictionary in this direction. So they try to approximately sample from the Gibbs distribution and use this correspondence to use that to approximate the partition function. So use sampling algorithms to give randomized algorithms for approximating the partition function. This is not, again, mostly we're talking about things I won't be talking about. So this is another one of those. What we will be talking about is the other method, which is of looking at the structure of mu and trying to exploit decay of correlations in mu to compute the partition function. So this I will give an example of. Okay, in fact, on the very next slide. So any questions so far? Okay, so I said I will give an example of one case where one can do something with the correlation decay. So here is the example of the anti-ferromagnetic Ising model. So what one can do for the anti-ferromagnetic Ising model is that, so let's fix the degree of the graph that we're going to be looking at. So arbitrary graphs of just fixed degree d. And then one can plot in this. So again, I'm plotting in this plane of beta and lambda, but for convenience I'm plotting log lambda and 1 over beta. So 1 over beta is between 0 and 1. You can plot a line, and I'll say where this line comes from, and everywhere above this line in this white region, when beta and lambda lie in this white region, and this line is just a function of d, there is a deterministic polynomial, there are FP tasks for approximating the partition function, the anti-ferromagnetic Ising model. So I'll say where this line comes from. And in fact, this is tight in the sense that if you're in the red region, just below the line, then the problem is NP hard. So this is also one of the results in the paper of Sly and Son that was cited earlier in the morning, that as soon as you're in this, so there's a line here, and it determines the complexity theoretic phase transition in the sense that on this side you have fully polynomial time approximation schemes. On the other side, even if you had a randomized approximation scheme, you would be able to solve NP-hard problems in randomized polynomial time. Okay, so where does this line come from? So it comes from correlation decay in the Gibbs measure, and in particular from the correlation decay in the Gibbs measure on the tree of the same degree. So if one looks at the anti-ferromagnetic Ising model, so if one looks at the anti-ferromagnetic Ising model on a tree of some fixed arity d, then it has the following. It shows the following phenomenon, which is as follows. So I look at the root, but I look at two conditional probability distributions at the root. One of them is obtained by fixing everything at at distance L from the root to plus. Just condition on those vertices to be plus, and then look at the conditional probability at the root. So that's the first one. And the second one is correspondingly obtained by just setting everything here to minus. And now I can look at what the difference between these two probabilities is as a function of L, as the distance at which I'm fixing vertices goes to infinity. So it turns out that in terms of beta and d, one can draw this line. So that was precisely that line, such that if you're above the line, so if you're above this red line, so that is like log lambda is bigger than that line, then the differences decrease exponentially in the length. So as L goes to infinity, the difference between the two probabilities goes to 0 exponentially fast in L. And as soon as you're on the other side of the line, in the red region, then the difference does not decay at all. So it remains bounded away from 0. And this property is what is used. So I won't go into the details, but this property is precisely what is used in coming up with the algorithm here. And similarly, this property of things not decaying is precisely what drives the proof of hardness. So it is this phase transition that sort of it does not only determine the complexity theoretic phase transition, it also underlies what goes into the two sides of establishing the phase transition. So this is one. So this is one example where a phase transition notion for the Ising model completely captures the complexity of an algorithmic problem related to it. So this is for the anti-ferromagnetic Ising model. What about the ferromagnetic Ising model? So the same picture that I showed you for the anti-ferromagnetic Ising model, that you have this tree and you can draw this curve and and like find out these critical lambda. All that works out also for the ferromagnetic Ising model, except that in this case, this line does not determine any complexity theoretic transition. So there is no. So one cannot prove this fact. One cannot prove such a thing that above the line you have algorithms and below the line the problem is hard, because in fact you have an algorithm everywhere. So this is a old result of Mark Cherem and Alistair here, that for any temperature parameter, as long as it's ferromagnetic, and any field parameter, there is a randomized a randomized Markov chain Monte Carlo based algorithm which will approximate the partition function of the ferromagnetic Ising model on any graph. It does not even require the graph to be bounded decay. So somehow, although this correlation decay phenomenon is still there on the tree, and this phenomenon sort of captured a complexity theoretic transition in the anti-ferromagnetic Ising model, it does not do so for the ferromagnetic. So, but let's just see what correlation decay can do in the ferromagnetic decay. So it's known that the ferromagnetic in the ferromagnetic case, you can get a deterministic algorithm on degree D graphs under this condition, and this condition precisely is so if I just go back to this curve. If 1 over beta is, so if in the ferromagnetic case beta is beyond this parameter d minus 2 over d, then the red line just terminates there. So every field at this point is sort of in the good region. So what is known for the ferromagnetic case, that in that situation, when all the fields are good, when even zero field is fine, one can get an FP task for approximating the partition function. But it uses correlation decay, and we know that correlation decay does not hold beyond this, so it cannot be pushed beyond that. So somehow the presence of this phase transition is an obstacle to using this method. So it's an obstacle to using the method of decay of correlations to get algorithm. But as I showed you, there is another algorithm that sort of just completely ignores this barrier and gives you a algorithm. So the question that one would want to ask is there a deterministic algorithm for approximating the ferromagnetic Ising partition function that matches Markov chain Monte Carlo methods, that can sort of also somehow ignore this phase transition? Okay. And in this talk, we'll try to address this question for bounded degree graphs. So, any questions? Okay. So, and yes, so the workshop is on zeros of polynomials, so this is where they come in. So it turns out that one can get such an algorithm, and one gets them using the properties of the complex zeros of the ferromagnetic Ising partition function. So what one can show is that as long as the graph is bounded degree and the field is bounded away from 1, so the field parameter lambda is bounded away from 1. So in the usual parameterization, this means that you don't have zero field. You have some finite, either positive or negative field. Then one can deterministically approximate the Ferromagnetic Ising partition function. And in fact, not just in the case of graphs, but also in the case of hypergraphs. And the hypergraphs case is also interesting because this Markov chain algorithm that I told you about sort of has in its proof some combinatorial considerations which depend very crucially upon the graph being a graph. It cannot easily handle hypergraphs. So we don't know even a Markov chain Monte Carlo algorithm as of now to approximate the hypergraph Ferromagnetic Ising partition function. But this method, based on deterministic approximation of zeros, does achieve that. And so as I will show more, it is going to be based on the Barwinockian philosophy that has been discussed several times today and already, and also on generalization of some results of Patel and Rex. But as an aside, I would also want to say is that these results, and there no suspense, they're going to be Liang theorems of some kind. If one can prove slightly sharper versions of them, then one also so this is for algorithms, but one can also get hardness results out of them. So I will say something more about them later on.
So, Piyush, what do you mean by the top second bullet?
This one?
Yeah.
So I didn't say that. So we can prove in fact that that the usual correlation. So in some sense there's the correlation decay algorithm for the anti-Ferromagnetic Ising model depend upon this technical condition that something called weak spatial mixing implies strong spatial mixing. This is not true for the Ferromagnetic Ising model in general. So that is what this means. So you can prove that weak spatial mixing for the Ferromagnetic Ising model with field does not imply strong spatial mixing. And hence the usual techniques for using correlation decay for coming up with algorithms will not work. Okay. So yeah. So what's the thing that we are going to look at? So this approximation algorithm is going to go in the following fashion. So remember that our goal is to get a 1 plus minus epsilon factor approximation to the partition function. That is like asking for a plus minus epsilon additive approximation to the log of the partition function. And how does one get that? So in hindsight, it's a very maybe obvious or simple idea, but underlies a lot of nice theory, that you just Taylor expand the logarithm around 0. So let's look at the Taylor expansion. We know that if we could somehow evaluate it up to some k terms, then the error decays like x. So if I want to evaluate it x, then the error depends upon the ratio, the k plus 1th power of the ratio between the point where I want to evaluate and the radius of convergence. And when is such a thing valid? Well, it's valid if the Taylor expansion itself is valid. And when is the Taylor expansion valid? Well, it's valid if log z is analytic, and that can be said in several ways. So this whole thing is valid if log z is analytic in the disk of radius r around 0. That is the same thing as zx being non-zero in that disk, and sometimes also written as z being stable with respect to the disk. There's different ways of saying the same thing in this setting. So somehow if we had such a result that the partition function does not vanish in some radius, then what does one do? So we have these CIs, and this is where the result of Barwinock comes in. So these CIs are closely related to the lowest k coefficients of z. So that's not surprising that the first k coefficients of the Taylor expansion of log are related to the first k coefficients of the partition function itself. And in some sense they sort of correspond to k-point correlations in the model. And based on this and results on zeros, Alexander Barwinock showed that you can get approximation algorithms for several counting problems. So in particular, so here are some results on zeros from which one can get algorithms. So for independent sets, we already saw Shearer and Scott and Sokal, who showed that for graphs of degree d, there are no zeros in a radius of about 1 over e times t. And for the Ising model, we'll see this in more detail later. There's a Liang theorem which says that when you're in the ferromagnetic regime, there are no zeros in the open unit disk, and in fact all the zeros lie on the unit disk. So just using this and the fact that you only need to take k to be about log n to get small enough error in this expansion, Barbanok's method shows that you can get quasi-polynomial time algorithm, so n to the log n algorithm, because just computing the k point correlations just by brute force when k is log n takes time about n to the log n. So the next advance that we are going to use is this very nice little Patel and Rex, which gave techniques for making some of these polynomial times. So when the graph is bounded degree, they showed that you don't really need to compute these correlations in a brute force fashion. One can do them in a somewhat more clever way, so that the runtime is only n to the log d rather than n to the log n. Decent. So that's going to be the general idea, but so we'll need to modify the results a little bit here, but before that, let me talk about the Liang theorem in more detail. So any questions before that I go into that? So I already mentioned the Liang theorem in the last slide. So here is theorem again in all its glory. So it says that when you're in the Ising ferromagnetic Ising regime, so beta is between 0 and 1, then the zeros of the partition function all lie on the unit circle. So it completely determines where they lie in some sense. And in particular, it's completely zero free in every region that sort of does not intersect the unit circle. So in particular, it's zero free in the open unit disk, which is what kind of thing one would need for Barbanok's method to work. So before I go into using this method, using the Liang theorem and its extensions for approximation algorithms, let me also mention just that one can show something. One can show this sort of curious fact about this, that the zeros are actually simple when the graph is connected, and interestingly, that this just the fact that the zeros are simple immediately implies that certain problems about computing sort of called means, so things like the magnetization, are number p hard if you want to do them exactly. So this is almost an immediate consequence of just the fact that the zeros are simple. So one can show that zeros are simple when the graph is connected, so somehow you can also use this theorem for some hardness. Okay. So let me just mention formally the results now. So I already said that we can, so just by the Liang theorem and the machinery of Patel and Rex and Barbanok, one can do the Ising model on graphs. So let's look at the Ising model on hypergraphs. So the way I define this is that now we have hyperedges, and for each, so now I can just index the configurations by the set S, which is the set of those pins that are plus, and then the field parameter behaves exactly as before, and the edge interaction parameter. So earlier you put a factor of beta whenever there was a difference, like whenever the edge was such that it had both a plus and a minus spin on the two endpoints. And similarly here, you put you put a beta factor for each hyperedge if it has both a plus and a minus spin. So that's the partition function. And what one can show is that there's an FP after computing this partition function on hypergraphs on maximum degree delta and maximum edge size k for all edge activities beta which lie in this region. Okay. So let's just look at what this region is. So we're even along negative beta here, which is sort of doesn't quite correspond to what I was earlier talking about probability distribution, but things work here. So on this side we have 2 to the k minus 1 minus 1. So it approaches 0 as k becomes large at this rate. Here it's slightly better, so the denominator sort of is, there's a cosine of pi over k minus 1 to the k minus 1. So it's always, so both these numbers are always less than 1 in absolute value. So it's always inside the. And what this is based on is a Liang theorem for hypergraphs. So this result is based on the following theorem that so you saw the Liang theorem for graphs. Now this theorem says that if you have a hypergraph where the maximum hyperedge size is bounded, so if it's exactly k, then the roots of the partition function as defined here lie on the unit circle, provided this same condition on beta holds. So as long as beta is in this range, you have the fact the zeros lie on the unit circle. And further, this is tight in the sense that if beta lies outside, then I can find a hyperedge, in fact just a single hyperedge of size k, where the zeros will not lie on the unit circle. Any questions? And so this proves the zero part. So yeah, so I mentioned in the Barvinok and partial direction method before. So to use the whole method for hypergraphs and for the Ising model, one needs to slightly generalize the partial index method. But that generalization, coupled with this extension of the Liang theorem for hypergraphs, gives you the algorithm that. Okay, so just to summarize what I said so far, so one can get using root location, and we'll see this more and more, I think, over the week in our talks, that using root location, one can get algorithm for approximate counting. For the Ising model on graphs, it was just Liang theorem plus partial index or some generalizations. And you can go beyond correlation decay. So we saw that correlation decay sort of stops at a certain beta. This works for all beta as long as the field is non-zero. And one can even generalize this to hypergraphs where one doesn't even have MCMC algorithms as yet. And all one needs is either this new Liang theorem and this generalization. In fact, one can also do the general two-spin system, the general hypergraph spin system that I mentioned earlier. And that depends upon another extension of the Liang theorem due to Suzuki and Fisher from the 70s. So this theorem strengthens the Suzuki-Fisher theorem in the special case of the hypergraph Ising. So one can use this generalization to even handle the earlier, this more general hypergraph Ising model that I mentioned. So my plan now is to just give a brief sketch of the proof of the Liang theorem, Asano's original proof, and followed by the proof of this extension. So before that, if there are any questions, okay. So let's look at the proof of the Liang theorem now. So we'll look at the Asano contraction, that was the Asano method, which was mentioned this morning, and then see how it generalizes to this hypergraph Liang.
Sorry, can I just ask exactly what is a hypergraph? It's just a product of spins, right?
Yes.
Effectively, that's all.
Yeah.
Okay, I'm not missing it.
So
this.
Sorry.
Sorry. A hypergraph is just a product of spins on, say, 3 sites or 4 sites or whatever.
So all that changes. So nothing changes on the spins. All that changes is how I measure the interactions. So for each hyperedge, a hyperedge can have more. So it's a higher order interaction. So a hyperedge can have more. So an edge has 2 vertices. A hyperedge can have k vertices.
Yeah, and what's the energy associated?
Yeah. So the energy. So I get a factor of beta whenever this hyperedge has both a plus and a minus spin.
Oh, both a plus and a minus.
Yeah. So it's like this. So I look at those. So my definition of cut edges is now those edges which contain both a plus and a minus spin. So S is a set of plus spins. So these are my so-called cut edges. So these are the edges for which I'll put a beta factor. Okay. And these edges are those which intersect both S and V minuses, so which have both a plus and a minus spin. Okay. And on the sides I do exactly the same thing as before. So I just multiply a lambda for all the plus spins.
And can you generalize the multivariate case both for beta and lambda?
Yeah, so there's already a generalization there's already a result of Suzuki and Fisher which gives a general Liang theorem for that setting. It's not tight in the sense, so it's not tight, for example, in this setting. So what their result would give you here is the same thing without the cosine. But it's more general. So it applies to the general hypergraph Ising where you have arbitrary spin vertices, but it puts some conditions on them. Those conditions are not tight.
So the general one, say, treats differently based on how many plus minus you have inside.
Yeah, it can do that. Yeah, it's allowed to do that. But yeah, it puts strong conditions. It can count the number of pluses and minuses and and apply to this, it will get this part exactly. So the Suzuki-Fisher theorem applied to this setting would get this. So this side would be the same, but this side would be missing the cosine.
So is there a hypergraph that achieves one of the terms?
Yes, this one is tight. So the hyper edge achieves this one. So this one is tight.
Can you maybe clarify what you mean beyond decay of correlations?
In the sense that I take a graph of degree d, and even if my beta and lambda are such that I can show that I can find a graph of degree d where there's no decay of correlations. In the sense that I can take, for example, a bipartite graph of degree d, which is an expander and has no decay of correlations, or like a family of such graphs, to be precise. And correlation decay has no hope of working on it in the sense that it just doesn't hold. So one can show that there are long-range correlations in this graph, however, or in this family of graphs. But this method would just work. It will give you an algorithm for approximating the partition function.
But it's not in contradiction with what slide.
No, but that is for anti-ferromagnetic Ising model. This is for ferromagnetic Ising. Okay, so let me just go through the Asano's proof of the Liang theorem, and then how that generalizes to our setting. So it turns out that, as in many cases, it's easier to prove the Liang theorem if you look at the multivariate generalization. So we'll say that a multilinear polynomial P has the Liang property if it has the following property, that it's non-zero whenever all its arguments lie on or outside the unit disk, and at least one lies strictly outside. So we'll say that P is Liang if it is non-zero whenever lambda i's are all on or outside the unit disk, and at least one is strictly outside. And one can similarly define the multivariate Ising model now. So the only difference from before is that now I'm allowed to have a different field for each vertex, and for each vertex, when it has a plus spin, I multiply its own field parameter, its own vertex activity parameter. So the earlier definition just had all the lambda is equal to lambda. And what Li and Yang proved, and we'll see Asano's proof this, is that whenever the edge activity is between 0 and 1, so whenever in the ferromagnetic regime, then this polynomial has the Liang property. Actually, technically speaking, I should also to be precise, I should also have G's connected to have this strong word. But yeah, so it has a Liang property in the sense that it does not vanish as long as at least one of the lambda is outside the unit disk, and all of them are on or outside. Okay, as long as G is connected. So let's just look at the general outline of Asano's proof. So Asano's proof it works in the following way. So let's look at this edge first. It shows, so for the Liang theorem, it shows the theorem for a single edge first. So the Asano's proof, so it will first show that the Liang theorem holds for the graph, which is just a single edge. And then what it does is to prove this theorem for some other graph, say the triangle, some other connected graph like the triangle. It first sort of thinks of each vertex as having been broken up.
No.
Yes, sir. So each vertex has been broken up, sort of into. So each vertex has some degree d, and it's sort of broken into d copies. Yeah. Broken into d copies, and you have the theorem for each of the single edges, and then it starts contracting vertices, and it shows. So it starts, for example, with these two edges, and then it shows that if the theorem holds for these two edges, it also holds for the graph, the V graph that you get by just collapsing those two. So you had the theorem holding individually for these two, and it will show that it will work also for. And then one shows that with these operations, you're starting with edges and just attaching new edges to the graph and collapsing vertices in the same graph, one can prove the theorem for any graph. And the structure of the proof for the hypergraph would also be similar. Again, we'll have to prove it for each uniform hyperedge. In the Asano case, was an edge, and then show that it is preserved. The Liang property is preserved under contraction of vertices. The only difference would be that the base case in this proving the theorem for the uniform hyperedge would be somewhat more complicated than the Asano proof, which I'll just go through. And the contraction proof would be more or less similar, somewhat similar. So let's just look at Asano's proof for the usual Liang theorem. Here is the proof for the single edge. So the partition function for a single edge, the multivariate partition function is just this. It's z1, z2 plus beta times z1 plus z2 plus 1. Okay. So this is and we want to show that this is Liang. So this has a Liang property. Okay. So what is that? So suppose that this was 0. If this is 0, then we can write something like this. So z2 is equal to 1. Let's say all the divisions are well defined. So z2 is equal to 1 plus beta z1 over beta plus z1 in absolute value. Okay. But what does this mean? Now when beta is between 0 and 1, so this is always a Mobius transform. It takes the unit circle to the unit circle no matter what beta is, as long as it's a real number. However, when beta is between 0 and 1, it takes the exterior of the unit circle to the interior. So when beta is between 0 and 1, so in the ferromagnetic setting, this transform takes the exterior. So if z1 was outside the unit disk, it takes that to the interior. And therefore, it cannot be the case when if these two are 0 that both of them are lying outside the unit disk. So if z1 was outside the unit disk, then because this transform is taking the exterior to the interior, z2 would have to lie on or inside the unit disk. So that's the theorem, and this also tells you why the theorem fails for the anti-ferromagnetic Ising model. Then beta would be bigger than 1, and now this transform takes the exterior to the exterior and the interior to the interior. So you don't get this. So the edge is already a counterexample, and you cannot even start the proof. And then so this is one step to prove it for the edge. How do you prove that? So there's this contraction step. So the contraction step in the Asano setting, so it's simple. So what you do is that you have some graph in which you want to collapse two vertices, and you have that the original graph has the Liang property, and you somehow want to say that the new graph where the two vertices are collapsed also has a Liang property. So what that corresponds to is something like this, that the original partition function, if I just look at the variables here, and a, b, c and d are polynomials in the other variables, correspond to the other vertices, then I'm going from the polynomial a z1 z2 plus b z1 plus c z2 plus d to a z plus d. So why is that? So these terms correspond to those configurations in which these vertices have different spins. But that is not going to be allowed if I'm going to collapse them. So only those configurations sort of survive where the two vertices have the same spin. So only this and this survive, and so you get to this. And how does one prove this? So this is quite nice. So if this polynomial has a Liang property, that means that this is not. So let's say that all the other values are fixed to things outside the unit circle. So if this is not equal to 0, whenever because it is Liang, so this is also not equal to 0 when both of them are outside the unit disk. But I can take z1 equal to z2, and so I get that az square plus bz plus cz plus d is also not equal to 0 when z is outside the unit disk. But this is a quadratic equation, and it has no roots outside the unit circle. So that means that the product of the roots has to be less than or equal to 1. But that is precisely the claim that az plus d has roots, has at least, so for it to be 0, z has to be less than 1. There's something I'm hiding here, that a has to be non-zero for all this to work. But that can be proved inductively. So the proof is, so there's no, so except for this, there's nothing being hidden here. It's that elementary for the graph case. What does one do for hypergraph? So this part will remain more or less the same. The complexity sort of comes in handling a single hyperedge, and that uses this slightly different criterion for the Liang property that is essentially a variation of David Ruel's characterization of a slightly different definition of the Liang property from a paper in 2010. And this says the following, that if you have a multilinear polynomial, and which has this property that, so it's a multilinear polynomial z1 to zn with all its coefficients non-zero. So for every subset, you have a non-zero coefficient. So this is the case in the Ising partition function, for example. And it is symmetric, so this is also the case in the Ising partition function. Then, if I look at, I just isolate one of the variables and look at the coefficient aj of that variable, then P has Liang property if and only if aj has a slightly stronger property that it's not 0 whenever all the other variables are on or outside the unit disk. So remember that Ly required that at least one variable has to be outside the unit disk. This is slightly stronger, that is saying that P is Liang if and only if these coefficients have a slightly stronger property that they are non-zero whenever all the variables that appear in them are on or outside the unit disk. And so this sort of basically what it tells you for a single hyperedge, for example, is that it's okay to just prove that the Liang property is true for AJ, so, or something like the Liang property, which is a slightly stronger version of the Liang property. For the leading coefficients, these coefficients that you get for each vertex, you just need to prove it for them, and then you get the Liang theorem for the whole hyperedge as well, because it's so now we have to look at what the leading coefficients of the single hyperedge look like, and prove the stronger Liang for that. So this, one can just do explicitly again. So one can write down what these AJs are. Yeah. One can write down what these AJs are, and this property that AJ has to be non-zero whenever the variables appearing in it are bigger than 1 turns out to be equivalent to 1 over beta being equal to this quantity, and this is now reduces to a, depending upon, so I think Alexander Barber likes to say that it's a middle school geometry problem or high school, something like that. So it reduces to some calculus or geometry, some kind of problem, and that's where the range of beta comes from. So you basically have to show that this cannot hold when these guys are. Okay, so that's, and the contraction proof sort of more or less proceeds along the same line as the original proof. With some places this characterization happened to be used. Okay, so just to summarize, so same as before, so one can use zeros of polynomials to get algorithms where correlation decay, the other main workhorse of getting deterministic algorithm, fails, and at least in one, and in several cases, even where Markov chain Monte Carlo algorithms are not known. So, and more recently, sort of correlation decay also has sort of struck back, and in some cases one can use correlation decay like arguments to prove absence of zeros. So, for example, so there are several. So starting with works of Peters and Rex, which Jan mentioned. So, but one of the things I would want to mention is this joint work with Jincheng, Yu analysis, which talks about Fisher zeros. So I talked so far about Liang zeros, which are zeros in the field parameter. One can also talk about zeros in the beta parameter, and much less is known there. And one thing that one can show, for example, using sort of correlation decay like arguments, is that in the correlation decay regime, so in the neighborhood of the correlation decay regime, the partition function does not vanish. So there's there are no Fisher zeros in a neighborhood of the Fisher of the correlation decay regime. Okay. So one thing that I would like to conclude with is that so I mentioned that there are these deterministic algorithms like correlation decay and zeros of polynomials, but they have this one disadvantage when compared to Markov chain Monte Carlo algorithms. Their dependence upon how far you are to criticality is very bad. So sometimes the Markov chain algorithm will also have some dependence upon how far it is from a phase transition boundary, but the dependence would be something mild, like the running time would be polynomial in n times a factor that goes to infinity as you approach the transition boundary. For these two algorithms, this distance to the critical value shows up in the numerator, so in the degree of the polynomial. So the degree of the polynomial goes up to infinity as you approach the transition boundary. So that one doesn't know how to handle, and so that's what I would like to conclude with. So is this just a matter of techniques, or is there some more fundamental reason that these deterministic methods cannot achieve this?
Questions?
So your running time also blows up when lambda is inverse polynomially close to 1, or it's just the degree?
Yes, it blows up. So the runtime is so 1 over lambda would so 1 minus so something like the degree of the polynomial will depend upon 1 over 1 minus 1 over lambda. So if you are in other words, if you are inverse polynomially close to lambda, then your runtime is exponential, so it's useless. You want to be at least constant. You want to be constant.
Go back to the single hyperedge slide. Just a bit quick. Yeah.
So So this is, you just write down AJ for a hypergraph with J vertices, and then you say what does it mean. So this is the other way around. So 1 over beta should not be equal to this whenever z. So AJ being equal to 0 is equivalent to this inequality holding. So what you want to show is that whenever all these arrays are on or outside the unit disk, this function avoids the point 1 over beta. And that is, so you can reduce it to some simple plane geometry problem. And that's where this range comes from.